Okay, let's start out by recalling some common derivatives. So the derivative of a constant is, of course, just 0. And the derivative of a monomial, x to the n, would be just bring the n down, x n minus 1. So for instance, the derivative of, say, 2x plus 5 to the 7 is equal to, well, we bring the 7 down, 2x plus 5 to the 6, but don't forget the chain rule, multiply by the derivative of the inside, so that would be derivative of 2x, which is 2. Another quick example here, derivative of, say, x to the 8 divided by 5, okay, is equal to 8x to the 7 over 5. And the reason I'm bringing this up as an example is because a lot of people ask me on the first day of class, why didn't we use the quotient rule right there? And the reason is because that over 5 is just, you can think of it like a coefficient, right? So we can think of this as, say, 1/5 times the derivative of x to the 8. So that's 1/5 times 8x to the 7, and there's your 8x to the 7 over 5. In reality, you actually can use the quotient rule. So let's see how that would play out. We would have, say, derivative of x to the 8 over 5. And using the quotient rule, we can take the derivative of the numerator, which is 8x to the 7, times the denominator, which is 5, minus the derivative of the denominator, which is 0, times the numerator, x to the 8, over the denominator squared. What we would get here is 8x to the 7 times 5 over 5 squared, and the 5 and a factor of 5 below would cancel, giving us, of course, 8x to the 7 over 5. So we actually did use the quotient rule. It would just be totally unnecessary in this situation. The derivative of the square root of x comes up enough times. So that is 1 over 2 rad x. And again, if you forget this one, it's really like taking the derivative of x to the 1/2, which is 1/2 x to the negative 1/2, and that's your 1 over 2 rad x business. All right, but this derivative comes up so frequently that it's good to just immediately jump to 1 over 2 rad x. Okay. For that matter, the derivative of 1 over x is negative 1 over x squared. And similar reasoning here, you can write it as an exponent, take its derivative, and you get that form, which is better written as negative 1 over x squared. So, all right, what about trigonometry here? Well, you definitely need to know these derivatives. Derivative of a sine is cosine, and the derivative of cosine is negative sine. Okay. And the derivative of tangent is secant squared. Okay. Now, while it's imperative that you really just know that quickly, because that's going to come up all the time this semester, to be a really good calculus citizen, you need to be able to recover information that in a pinch you may have forgotten or you're not quite confident about. So let's pretend like we forgot the derivative of tangent is secant squared. How could we use the knowledge that we know about calculus to actually generate that information? Okay, well, we just start playing. So this is the question, derivative of tangent of x. Well, we can write tangent as sine of x over cosine of x. And now we can use the quotient rule on this guy. So we can say, well, the derivative of the numerator, derivative of sine, is cosine of x times the denominator minus the derivative of the denominator, which is negative sine of x, times the numerator. And that's all divided by the denominator squared. So what we have is, in the numerator, cosine squared of x plus sine squared of x all over cosine squared of x. And cosine squared of x plus sine squared of x is 1 over cosine squared of x. So indeed, that's secant squared of x. Ah, yes. And now that hopefully helps you remember what the right answer is. Okay. Now, you don't want to be using up time on an exam or a quiz recovering basic information like that. So you obviously should look at this and go, yeah, it's really useful to know the derivative of tangent. All right, so what is the derivative of cotangent of x? Well, that is negative cosecant squared of x. All right, and what is the derivative of secant of x? Well, that is secant of x times tangent of x. Okay, again, all of these can be recovered using the technique we just did on tangent by writing things in terms of sine and cosine and using the quotient rule as needed. Okay, before we write down the derivative of cosecant, which I'm sure many of you know, I would like to point out a certain pattern that's emerging here. Okay, all 6 trig functions can be paired off in what are called cofunctions. So sine and cosine are cofunctions, tangent and cotangent are cofunctions, and secant and cosecant are cofunctions. So when we say sine and cosine are cofunctions, what we're really saying is that sine and cosine satisfy this identity. Okay, it doesn't actually matter where you place the function, so we could put cosine on the left and sine on the right here, or vice versa. Okay. Cosine and sine are a cofunction pair because we have this set of identities. And the same is true for tangent and cotangent. Tangent of x is cotangent of pi minus 2 minus x. Cotangent of x is tangent of pi minus 2 of pi over 2 minus x. Okay, and of course, secant and cosecant satisfy this. Okay, the cofunction pairings are really easy to remember by just thinking of their graphs. Sine and cosine have almost the same graph, but they're just horizontally offset by pi over 2, and sine and cosine are cofunctions of each other. The same is basically true for tan and cotangent. They both have this sort of vertical swooshy graph that are offset by pi over 2. And cosecant and secant, you can see, also have basically the same shape of graph with that slight offset of pi over 2. So if you understand the graphs of these functions, just in terms of their basic shapes, then you'll easily remember how to pair off the functions as cofunctions. Now, why am I making a big deal about this in calculus? Well, if f and g are cofunctions, meaning they satisfy this identity one way or another, and we take the derivative of both sides of this, then using the chain rule, a negative is going to come out. So we'll multiply g prime by -1. And what this is telling us is that the derivatives are going to be negative cofunctions of the derivative of the other. Okay, so take a look at tangent and cotangent, for instance. They are cofunctions, and their derivatives, secant squared and cosecant squared, are cofunctions, but one of them has a negative and one of them is positive. It's actually the same for sine and cosine. So sine and cosine are cofunctions, and if you know the derivative of one, then you'll know the derivative of the other by just replacing it with a cofunction and putting a negative in front. Which means if you know the derivative for secant, which is secant times tangent, you can deduce the derivative for cosecant. So the derivative of cosecant will be the negation of the derivative for secant with these two factors replaced by their cofunctions. Okay. Now this may have been a roundabout way of getting at a simple fact that you already knew from Calculus 1 that you could figure out easily using the quotient rule. And yes, that's all true. But I think it's very important to have a full picture of what's going on in even the simplest situations. So that will only help you understand how to put things together in calculus. Okay, let's look at a few more derivatives. So we have the derivative of e to the x, which is e to the x. Okay, that's my favorite derivative, because even if you forget to take the derivative, you still get the right answer. Now, what if we have some base that's not equal to e? Well, you need to know this one. That's just, say, a to the x times natural log of the base. Okay, so for instance, the derivative of 5 to the x is 5 to the x ln of 5. All right, there are several ways that you can recover this information. So one is you can use logarithmic differentiation. So let's suppose that we don't remember the derivative of a to the x. We seek dy dx, right? There's a sneaky move where you take the ln of both sides, and that allows you to bring the exponent, which is x, down in front. Now you can find the derivative implicitly. So the derivative of ln of y is 1 over y times dy dx, chain rule. And the right-hand side, x times a coefficient. Ln a is just a constant, so a constant times x, its derivative is just that constant. So we have ln of a. Okay, solving for dy dx. That y comes over, we get y times ln of a, and y was originally a to the x, so our derivative is a to the x ln a, okay, from which we deduce the original question. There we are. So there is another way to work out this derivative without using implicit differentiation, and that is remembering this fact here that a to the x is equal to e to the ln of a to the x, okay, which is equal to e to the x ln of a, which means that the derivative of a to the x is equal to the derivative of e to the x ln of a. Now, why is that helpful? Well, because we know how to take the derivative of e to the stuff. It's just e to the stuff. So our answer will be e to the stuff times the derivative of the stuff. So this is using the chain rule times the derivative of x ln of a. But that's just x times a constant, so it'll just be the constant. So we get e to the x ln a times ln of a. And what is e to the x ln a? Well, that's e to the ln of a to the x, which is a to the x. So the whole point of going through all of these little motivations and quick proofs on the side here is just to, well, for one thing, my intention here is to kind of bring up to the surface facts from algebra, pre-calculus, and Calc 1 that you may not have seen in a while. So I'm just sort of helping you remember what drawers things are in your mind. But also, it's important that you understand that you have the tools to recover all this information. I haven't actually shown you any new magical moves here. I've just demonstrated how you can use what you already know about algebra and pre-calculus and calculus to recover information that you may have forgotten. Okay. Of course, you could save yourself a lot of trouble by just knowing the derivative of a to the x is a to the x ln of a. Okay, the derivative of natural log of x is 1 over x. And the derivative of log base a of x, where a is a constant, is 1 over x ln of a. Okay? That one's actually really easy to prove. I'm not going to go through a full thing, but you simply use the change of base formula to write out this as ln of x over ln of a. So the derivative of this thing is like 1 over ln of a times the derivative of ln of x, which is 1 over x. And so we arrive there. What about the derivative of x to the x? Okay, well, let me tell you a couple of wrong ways of thinking about it. I often see the answer being, well, let's bring the x down from the exponent and subtract 1. So you get something like this. X comes down, x to the x minus 1. Which, by the way, just works out to x to the x when you apply laws of exponents. So it's like saying that x to the x is its own derivative, which is patently false. Okay, what else have I seen? I've also seen treating this as a base raised to the x. So that'd be, oh, it must be x to the x times ln of the base, right? Like we took the derivative of a to the x. That is also false. However, it does turn out to be actually just the sum of those two things. But the way we approach this, and the problem is, by the way, that we have x in the base and the exponent. So this situation applies if you have a function of x raised to some other function of x, right? Sine x to the rad x, for instance. Then you have to do logarithmic differentiation. So we actually just did it a moment ago, but let's quickly do it here. So we're going to let y equal x to the x, and our goal is to find the derivative of y. Okay, so we're going to take the ln of both sides, and I brought the x down in one move there. And now we go 1 over y times dy dx, taking the derivative implicitly. On the right-hand side, we need the product rule. So the derivative of x is 1 times ln of x plus x times the derivative of ln of x. Okay, so that actually is just 1 there, that term. And so we get dy dx, bringing the y over, but y is x to the x. So there is our answer. So our conclusion is that the derivative of x to the x is x to the x ln x plus 1, which is actually the sum of the two false answers that we saw earlier. It's kind of neat. Well, this is an interesting one. What if the base of the logarithm depends on x? Okay, well, here you would need the change of base formula. So we could say this is equal to the derivative of ln of the numerator divided by ln of the denominator. And before we take that derivative, let's note that ln of e is 1. So this is like the derivative of 1 over ln x. No problem. Now it's just the quotient rule at this point. Okay, so the derivative of the numerator is 0 times the denominator minus the derivative of the denominator, which is 1 over x, times the numerator, all divided by the denominator squared. So what we get is negative 1 over x times ln of x squared. By the way, I use those 3 dots frequently in my notes, and they mean therefore. All right, let's look at a few more derivatives before moving on. You do need to know the derivatives of the inverse trig functions. Derivative of inverse sine is 1 over radical 1 minus x squared. And the derivative of inverse cosine is actually just the negation of that. Derivative of inverse tangent, this one actually comes up a surprising number of times in Calc 2. Derivative of inverse tangent is 1 over 1 plus x squared. Okay, and the derivative of inverse secant is 1 over x radical x squared minus 1. Okay, it will behoove you to know those ones. They will come up just often enough where it becomes useful for you to know those ones. But as always, can you recover them if needed? Okay. Yes, you have the ability, right? None of this information just appeared chiseled into a rock, right? That we just discovered one day and said, hey guys, look, now we know the derivative of inverse tangent. I mean, somebody had to be the first person to say, what is the derivative inverse tangent? And then using the tools of calculus, actually figured it out. And we can do that right now. In fact, we should do that right now. All right, well, this process is very similar to logarithmic differentiation. So we want to find the derivative inverse tangent. We pretend like we don't know it. What we're going to do is we're going to let y equal inverse tangent of x, which reframes the problem to we seek dy dx, right? We seek the derivative of y here. Okay, but writing y equals inverse tangent of x allows us to rewrite this as tangent of y equals x. And we know the derivative of tangent, which means we can now find dy dx implicitly. So the derivative of tangent is secant squared. Chain rule gives us the dy dx here. And we get 1 on the right. Isolating dy dx gives us cosine squared of y, right? That's what dividing by secant squared will do. So we have cosine squared of y. Great, we found dy dx, except that's really unsatisfying because we, the people trying to solve the problem, invented the letter y. The original problem is asking about inverse tan of x, which should be some expression involving x. So we need to kind of convert this back over to x's. And the way we do that is by drawing a triangle. Okay, if we consult this line right here, tangent of y equals x, that tells us that y is the angle and its tangent value is x, which means we can label the sides of this triangle x over here, 1 over there. So indeed, tangent of y is x. Using the Pythagorean theorem, we can find this missing side here, 1 plus x squared under a radical. Now you can read off of the triangle any trig function of y, sine, cosine, tangent, whatever. We need cosine and we need to square it. So here, our dy dx is the square of cosine, right? Well, cosine, adjacent over hypotenuse, being squared, of course, gives us 1 over 1 plus x squared, which is the derivative of inverse tangent. So we win. Okay, you also need to know the hyperbolic functions from Calc 1. So that's like hyperbolic sine, hyperbolic cosine. So you need to know their exponential definitions. For instance, sinh of x was defined to be e to the x minus e to the negative x all over 2. Cosh of x, hyperbolic cosine, is e to the x plus e to the negative x all over 2. Now, if you understand those two definitions, and you understand the basic reciprocal identities from trigonometry, then you can conjure up the definition of all the other hyperbolic functions. For example, hyperbolic tangent, or tanch, or tan, is just sinh over cosh, which would be the numerator from sinh, divided by the numerator from cosh. The 1/2s cancel. So there's the definition of tanch. Okay, and hyperbolic cosecant, or cosech, that's like 1 over sinh, which would be just the reciprocal of sinh, wouldn't it? Hyperbolic secant, or sech, is 1 over cosh. And finally, hyperbolic cotangent, or coth, is 1 over tanch. Just the reciprocal of tanch. So there we are. If you know sinh and cosh, then you can recover the definition of all of them. Now, a few derivatives that are worth knowing here are that the derivative of sinh is cosh, the derivative of cosh is sinh, and the derivative of tanh is sech squared. These are all very, very easy to predict based on your knowledge of trig. And there we are. All right, so note that there is no negative for the derivative of cosh. It comes out to positive sinh, not negative sinh. So that is just a consequence of the hyperbolic functions behaving sort of like trig functions, but not quite, in almost a frustrating way. So you can always recover the information you need by just appealing to the definitions of whatever hyperbolic function you're working with and applying the derivatives to the exponential in the definition. Okay, toward the end of Calc 1, you encountered antiderivatives. So let's take a look at a few of those. So this is basically like asking the question, what function has x to the n as its derivative? And we know the answer to that, you may recall, involved simply adding 1 to that exponent and then dividing by that new number. And of course, general antiderivatives have a constant added. Now this particular one only applies if n is not equal to -1, right? So as a quick example, if you're taking the antiderivative of, say, 3x to the 7, then that would give you 3x to the 8 divided by 8 plus c. And of course, just taking the derivative of 3x to the 8 over 8, you would get back to 3x to the 7, confirming your answer. In the case where n does equal -1, that is this guy right here. This is x to the -1. And we know that we had a special function for that, which is the natural log of absolute value of x as its antiderivative. Okay, we also can look at this one. This comes up quite often. Antiderivative of the square root of x. We can interpret that as the antiderivative of x to the 1/2, of course. And then using the power rule above, we can say, well, let's add 1 to 1/2, which would be 3/2, and divide by 3/2. And that's a pretty ugly way to leave our answer. So we will typically just go 2/3 x to the 3/2 plus c. Or if you want to write it in terms of radicals, 2/3 x rad x plus c. Okay, and you can distribute an integral across a sum. So you get, this is like the antiderivative of cosine plus the antiderivative of secant squared. And again, the fundamental question whenever you're working out one of these is, what function has cosine as its derivative? And what function has secant squared as its derivative? Both of those are answerable. Sine has cosine as its derivative, and tangent has secant squared as its derivative. So there we are, final answer. Sometimes you need to do a little manipulation. So take a look at this guy. All right. The wrong thing to do is to just sort of barrel in and say, well, that must be this thing divided by this thing. Okay, don't do that. You would never take a derivative that way, right? If you were taking the derivative of x plus 1 over rad x, I mean, you would use the quotient rule, right? The same with products. If there's some special rule that you would need taking a derivative, product rule, quotient rule, chain rule, then if you're taking an antiderivative or working out an integral like this, then you would need some analogous technique, right? And we don't know that many techniques yet. The point is just to remember that there are special techniques. You cannot just distribute an integral any which way you want. So for this one, we can just do some basic manipulation and say, well, this is like x over rad x plus 1 over rad x, right? And each of those pieces simplifies. So we have, say, x to the 1/2 plus x to the negative 1/2. And I'm writing them with the fractional exponent because it's easy to use the power rule at that point. So this becomes x to the 3/2 divided by 3/2 plus x to the, okay, negative 1/2 plus 1 is positive 1/2. And we're dividing that guy by 1/2 plus c. Let's clean it up. That would be 2/3 x rad x plus 2 rad x plus c. Okay, very nice. What about this one? Antiderivative of tangent squared. All right, well, we can't think of a function maybe off the top of our heads whose derivative is tangent squared, but we can manipulate this. So tangent squared, there is a Pythagorean identity involving tangent squared, and that is secant squared minus 1. Okay. And writing it this way, we can see, well, we know the antiderivative of secant squared is tangent, and the antiderivative of 1 is x. Let's add our constant, and we're done. Okay, so let's quickly talk about the Pythagorean identities and trig in general. I am functioning as though you are an expert at trigonometry. This is Calculus 2, okay? So you just need to know your trigonometry. If you're watching this and it's before the beginning of the semester, and you wanna do one thing before the semester starts to really put you in the best position, review your trigonometry. Okay, that's know your unit circle values and know your trig identities. All right, all the principal ones. So let me help right here. How did we know right away that tangent squared was secant squared minus 1? Well, there's the Pythagorean identities. Cosine squared, I'll just use theta, plus sine squared theta equals 1. You really have to just know that one, of course. But there are two more. There's 1 plus tangent squared equals secant squared. And that one has a mnemonic I tan secretly. Okay, so if you just remember the mnemonic I tan secretly, and you understand the structure you're expecting, 1 plus tan squared equals secant squared. And that's the one we used, although we had to quickly move the 1 over for secant squared minus 1. The third Pythagorean identity is 1 coat in the closet. So that would be 1 plus cotangent squared equals cosecant squared. 1 coat in the closet. All right. So there we go. Now you'll never forget them.